Welcome to part 8 of our video series in support of hypothesis testing. In this video, we are going to review the chi-square test statistic involving the population variance sigma squared. We're going to do a visual review of the chi-square distribution. We will also review the F test statistic involving the ratio of two population variances from independent population, and also do a visual review of the F distribution. I'm Renee Clark from the Swanson School of Engineering at the University of Pittsburgh. Okay, for inference on one variance sigma squared, okay, we know that a point estimate for sigma squared is S squared, or the sample variance, okay? So if we take a sample out of a normally distributed population, then this statistic or random variable, which is n minus 1 times the sample variance over the population variance, has a chi-squared distribution, which we write as chi-squared, with n minus 1 degrees of freedom, okay, or sample size minus 1 degrees of freedom. Note that our population must be normally distributed. When using the chi-square distribution for this inference. Okay, let's do a visual review of the chi-square distribution. Okay, recall that the chi-square distribution, as shown here, it's a continuous distribution. It is skewed to the right because it has a long right tail to the right. Okay, if I were to identify this point right here along the x-axis, that's a particular critical value of the chi-square distribution, that is actually labeled as chi-squared sub alpha over 2. The reason being is because this particular critical value is showed as having alpha over 2 area to the right in the picture. And remember that the subscript on the critical value by convention refers to area to the right of it under the curve. Okay, so likewise, this value right here in red along the x-axis is designated as chi-squared sub 1 minus alpha over 2. And the reason for that is you will notice that in the picture it has alpha over 2 area to the left of it under the curve. That means it must have area 1 minus alpha over 2 to the right, since total area under the curve must equal to 1. Okay, so when we are doing inference with one variance, this is our null hypothesis versus the two-sided alternative that the variance is not equal to some hypothesized variance. Okay, but to proceed with a proof by contradiction, in order to prove the alternative, we have to assume the null to be true. Therefore, we will insert the null hypothesized value for sigma squared into our chi-squared test statistic. Okay, and this quantity becomes our chi-squared random variable or test statistic for performing inference on the variance sigma squared. So we have a hypothesized value for sigma squared in the denominator. Okay, let's next talk about inference for the ratio of two variances from two independent populations, or sigma 1 squared over sigma 2 squared. Okay, so we know a point estimator from the past. We know the point estimator for sigma 1 squared over sigma 2 squared is S1 squared over S 2 squared, okay? Or the ratio of the two sample variances from those populations, okay? So if we take a sample from each of two normally distributed independent populations, okay, then this particular statistic here, okay, which is the ratio of the sample to the population variance in the first population divided by the ratio of the sample variance to the population variance of the second population, that particular random variable or statistic has an F distribution, right? And this can actually be written in that way as well, just by some simple rearrangement of the terms. Okay, this random variable has n1 minus 1 and n2 minus 1 degrees of freedom, so 2 different degrees of freedom. But like the chi-square distribution, each population from which we're sampling to do this inference must be normally distributed. Okay. So when using the F distribution in this way, your populations must be normally distributed. Okay, so again, let's do a visual review of the F distribution. This point right here along the x-axis, which is a particular critical value of the F distribution, would be labeled or should be labeled as F sub alpha over 2 because it is shown as having area of alpha over 2 to the right. And you'll remember the subscript on the critical value by convention represents area to the right. Okay, so likewise, this particular critical value of F at that point along the x-axis should be labeled as F sub 1 minus alpha over 2, okay? The reason being is because it is shown as having alpha over 2 to the left of it under the curve. So if it's got alpha over 2 area to the left, that means it must have 1 minus alpha over 2 area to the right of it under the curve, right? Because the total area under the F curve must equal 1. Okay, in performing inference for the ratio of two variances, sigma 1 squared to sigma 2 squared, okay, this is our typical null hypothesis, that the two population variances are equal. Okay, another way to write that is that the ratio of sigma 1 squared to sigma 2 squared equal to 1, simply by dividing by sigma 2 squared on each side of the equality. Or equivalently, we could write this as sigma 2 squared to sigma 1 squared equal to 1. Either way, in which case you would be dividing by sigma 1 squared on each side of the equality. Okay, so in proceeding with a proof by contradiction, what we are going to do is we are going to insert the null hypothesized information into our test statistic. Okay, so we saw on the previous page that this is our test statistic distributed according to the F distribution involving our two population variances. Okay, it can be written either way, but what we're going to do is when we substitute this information in about the ratio of the two population variances, we're going to get a cancellation. Okay, if that hypothesized ratio is 1, that's going to cancel. Or alternatively, if you're going to look at it the other way, it's going to cancel. So what you're ultimately left with is that the F test statistic can be simplified to the ratio of the sample variances, S1 squared over S2 squared. Probably the simplest test statistic we've seen thus far. Okay? This, of course, will have N1 minus 1 degrees of freedom and N2 minus 1 degrees of freedom. two separate degrees of freedom. We wish to thank the National Science Foundation under Grant 233-5802 for supporting our work. Thank you for watching.